Hello and welcome to Lecture 4 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to look at the notions of entropy and thermal equilibrium. Okay, so last time we made sense of this funny principle, which states that the state property of a macroscopic system in equilibrium is always the most probable. And we learned that this principle is true because in a macroscopic system, there are so many more states having the most probable property than any other property that makes it virtually guaranteed that the system will indeed have the most probable property. Now this time we're going to apply this principle to the very important problem of thermal equilibrium. So we're going to consider two systems, system A and B, and together they form the total system. So we're going to consider that the total system, A and B together, is isolated from the universe, but that system A is in thermal contact with system B. When I say that the two systems are in thermal contact, I mean that they can exchange energy. But since the total system is isolated from the universe, they can exchange energy only between themselves. So A can exchange energy with B, but only with B, and B can exchange energy with A and only with A. And to apply this principle to this problem, we need to define this very important function, which is called the multiplicity. So G here is the multiplicity, and the multiplicity is a function of the properties. At this moment, the only property we are looking at is the energy. So G is a function of the energy U. And by definition, the multiplicity, G, is the number of states having energy U. Now, since the total system is formed by systems A and B, we can define multiplicities for the systems A and B independently. So Ga of Ua is the multiplicity of system A. In other words, it is the number of states of system A having energy Ua. And Gb of Ub is the multiplicity of system B. So as an example, let's suppose again a system A composed of two coins, just like we did in the previous lecture. So these are the four states of the system, the four possible combinations of heads and tails. And let's suppose again that we ascribe 0 units of energy to heads and 1 unit of energy to tails. So this state, HH, we have two heads, so 0 units of energy. HT, we have one tail, so 1 unit of energy. TH, 1 unit of energy. And TT, 2 units of energy. So that means that the multiplicity of system A evaluated at the energy 0 is 1 because we have only one state having the energy 0. On the other hand, the multiplicity of system A evaluated at the energy 1 is 2 because we have two states having energy 1, the state HT and the state TH. And the multiplicity of system A evaluated at the energy 2 is again 1 because we have only one state of the system having energy 2. So our job now is to make a list of states of the total system, the combination of system A and B, assuming energy conservation. So to show how we can make this list, we're going to use again an example. So we're going to suppose that system A has 2 coins, system B has 3 coins, and we're going to assume that the total energy is U naught equal 2. So U naught is the total energy, the energy of the total system, of system A and B together. So we begin by making the list of states of system A and of system B. So system A still has only 2 coins, so this is the same list we have just seen. These are the multiplicities. System B has 3 coins, so these are all the combinations of heads and tails of 3 coins, and these are the corresponding multiplicities. So for example, the multiplicity of system B evaluated at the energy 1 is 3 because we have 3 states, these 3 states having 1 unit of energy. The multiplicity of system B evaluated at energy 2 is also 3 because again we have another 3 states having 2 units of energy and only one state having 3 units of energy, so that's why the multiplicity is 1. Only one state having 0 units of energy, that's why the multiplicity evaluated at energy 0 is 1. Now, to make the list of states of the total system having the total energy that we chose as an example, we need to check how we can combine states of system A with states of system B so as to have a state of the total system with the total energy. So for example, let's check which states of system B can combine with this state, HH of system A, to form a state of the total system with energy 2. Since the energy of this state here is 0, this state can only combine with states of system B having energy 2. So these are the 3 states of system B having energy 2. So these are the 3 states of the total system. So this is one state of the total system, this is another, this is another. Notice that all of them have energy 2, and these are the 3 only possible states of the total system which were formed with combinations of this state HH of system A with states of system B. Now if we look at this state here, HT, now this state has energy 1, has one tail up. So this state can only combine with states of system B having 1 unit of energy, and these are the states having 1 unit of energy. Now we have the states of the total system formed by combinations of this state HT of system A with states of system B. Notice that again all of these states have energy 2 as expected. As for the state TH, it also has 1 unit of energy, so it can combine with the same states of system B that were combined with the state EHT. So these are the states of the total system formed by combinations of state TH with states of system B. And finally, the state TT can only combine with this state of system B because the state TT has 2 units of energy, and this is the only state of system B having 0 units of energy. Okay, so now we have the list of states of the total system having 2 units of energy. So it makes sense that all states of the total system have the same energy because we are assuming that the total system is isolated from the universe. And we are also assuming that energy is conserved. So the energy of system A can change because some states have 0 units of energy, some states have 1, and some states have 2. The energy of system B can also change, but the total energy is fixed because we are assuming that energy is conserved. Now we need to define the multiplicity of the total system. So T here is for total. So recall that the multiplicity of system A is defined as a function of the energy of system A, and the multiplicity of system B is defined as a function of the energy of system B. But it does not make sense to define the multiplicity of the total system as a function of the energy of the total system, because this energy is conserved. All states of the total system have the same energy, so it does not make sense to define the multiplicity as a function of the energy of the total system. So instead of doing that, we define the multiplicity of the total system as a function of either the energy of system A or the energy of system B. I chose the energy of system A, but it does not matter. So GT of UA is defined as the number of states of the total system where the system A has energy UA. So to find this multiplicity, to find the multiplicity for a given energy of system A, we need to count in how many states of the total system system A will have the energy UA. So for example, let's say we want to evaluate the multiplicity of the total system at the energy UA equals 0. So we come to our list of states of the total system and we identify in which states of the total system system A has 0 units of energy. So it's this state, and this state. In these 3 states, system A has 0 units of energy. So the answer is 3. If you want to know gt of UA equal 1, we need to identify in how many states of the total system system A has 1 unit of energy. And these are these 6 states within the green box. And for gt of UA equal 2, we find that its multiplicity is 1 because only one state of the total system, in only this state, system A has 2 units of energy. Now we want to express the multiplicity of the total system in terms of the multiplicity of system A and the multiplicity of system B. So this function is the number of states of the total system having the system A with energy UA. Now, since there are GA of UA states of system A with energy UA, so this statement comes directly from the definition of this function. And since each one of these states can combine with states of system B having the complementary energy, in other words, the total energy minus the energy of system A, it follows that the multiplicity of the total system evaluated at the energy UA is equal to the product of the multiplicity of system A with this energy times the multiplicity of system B with the complementary energy. So for example, coming back again to the evaluation of the multiplicity of the total system at UA equals 0. So we know that the result is 3. And the result is 3 because we have one state in system A having 0 units of energy, this state, and this state can combine with 3 states of system B having the complementary energy. So we get this number 3 because we have one state in one system and this state can combine with 3 states of the other system. Recall that this is 3 because this is the number of states of system B having 2 units of energy, having the complementary energy. Now let's check the number of states of the total system where system A has 1 unit of energy. First we ask how many states of system A have 1 unit of energy. The answer now is 2, these 2 states. And now we ask how many states of system B can combine with each one of these 2 states. The answer is the number of states of system B having 1 unit of energy, having the complementary energy. And the answer now is 3. So we have 6 states of the total system where system A has 1 unit of energy. It's these 6 states here, and that's because we have 2 states of system A having 1 unit of energy, and each one of these can combine with 3 states of the system B having the complementary energy. And if we do the same for 2 units of energy in system A, we find that there is only one state of the total system where system A has 2 units of energy. because we have only one state in system A having 2 units of energy, and this state can combine with only one state of system B because only one state of system B has the complementary energy, which in this case is 0. So in general, the multiplicity of the total system evaluated at the energy UA is given by the multiplicity of system A evaluated at the same energy times the multiplicity of system B evaluated at the complementary energy. Now let's take a look at how this example of coins relates to a physical situation. So physically, the elements, which here are the coins, they can exchange energy, and they can exchange energy within the same system or across systems. So in our example, that would mean that the coins can exchange energy. So suppose we take a measurement and find the total system to be in this state, and then this coin and this coin exchange energy. So that means that the new state of the total system will be this one. And since the coins keep exchanging energy, every time we take a measurement in the total system, we find it to be in a different state. And in practice, we cannot predict how the elements exchange energy. So we cannot predict which state of the system we are going to find. So what do? We assume that all states are equally probable. This is the fundamental assumption of statistical physics. So in our example, we have 10 states. So we assume that we're going to find this state in 1 out of 10 measurements, this state in 1 out of 10 measurements, this state in 1 out of 10 measurements, and so on. Now notice that even though all states of the total system are equally probable, the probabilities of the properties are not the same because more than one state can have the same property. Now the property we are interested in is the energy of system A, and these energies are not equally probable. So the probability of system A to have 0 units of energy is 3 out of 10 because in 3 states of the total system, system A has 0 units of energy. The probability that we're going to find system A having 1 unit of energy is 6 out of 10 because in 6 states of the total system, system A has 1 unit of energy, and the probability of energy equal to is 1 out of 10 because only this state here, in only this state of the total system, system A has 2 units of energy. So every time we measure the energy of system A, we're going to find a different number. But 3 out of 10 measurements, we're going to find it to be 0. 6 out of 10 measurements, we're going to find it to be 1. And 1 out of 10 measurements, we're going to find it to be 2. And we have a most probable energy. The most probable energy is 1 because this energy has a probability of 6 out of 10. Okay, so we have a most probable energy. The most probable energy is UA equal 1, 6 out of 10. But this probability is not overwhelming. It's only 6 out of 10. It's only 60%. This is not an overwhelming probability because our system is not macroscopic. In this example, we have a small system, only 5 coins. If we had a macroscopic system, then the probability of the most probable energy would be very, very, very close to 1. It would be almost sure, virtually sure, that we would find system A with the most probable energy. So now we're going to extend this idea to macroscopic systems, and take advantage that in macroscopic systems, the most probable energy will be overwhelmingly more probable than the other energies. So let's suppose then that we still have a system A and system B that are interacting. The total system is isolated from the universe, but now we have macroscopic systems. Now we suppose that a daemon draws the list, makes the list of the states of the total system, following the same logic we've just developed, but now the list is huge, so that's why we need a daemon. And now we ask, what is the energy of system A? Since now the system is macroscopic, the question, what is the energy of system A, reduces to the question of what is the most probable energy, because now the probability of finding system A having the most probable energy is almost 100%, is virtually equal to 100%, because this probability of the most probable energy is overwhelmingly higher than the probability of finding system A having any other energy. So our question, what is the energy of system A, is reduced to the question, what is the most probable energy? And to answer this question, all we need to do is to identify which energy has the most states, because the energy having the most states is the most probable energy. Since the number of states is given by the multiplicity, mathematically we are asking which value of energy, UA, maximizes the multiplicity. And we know from calculus that at a point of maximum, the derivative vanishes, so it's zero. So the question, what is the most probable energy, is reduced to the question, what is the energy with most states, which is reduced to the question, what is the energy that maximizes the multiplicity, which is reduced to the question, what is the energy at which the derivative of the multiplicity with respect to the energy is zero. And notice that we are treating the energy as a continuous variable here, even though we know that the energy is discrete. And what allows us to treat this discrete variable as continuous is the fact that the systems are macroscopic. So the energy levels are so close to each other that we can treat the energy as a continuous variable. Okay, so we found that when system A is in thermal contact with system B, then the energy of system A is the energy at which this derivative is zero. So now we can evaluate the condition at which this derivative is zero. So to do that, we're going to express the multiplicity of the total system as the product of the multiplicity of system A and the multiplicity of system B, as we have just seen. And with this product, we can evaluate this derivative using the chain rule. So according to the chain rule, the derivative of this term is the derivative of the first term times the second plus the first term times the derivative of the second. And recall that we are looking for UA that satisfies this condition. In other words, we want to find the energy at which this sum is zero. Also recall that this term is the energy of system B, and it comes from the condition of energy conservation. So we can express this derivative in terms of the derivative with respect to the energy UB, again using the chain rule. So this derivative is the derivative of GB as a function of UB with respect to UA. Then we use the chain rule to express this derivative in terms of the derivative with respect to UB. Since the energy of system B is the total energy, which is fixed, minus the energy of system A, the derivative of this variable with respect to this one is just -1. So this term here is -1, which follows that this derivative, this term, is equal to this derivative. So using this expression over here, we get this condition. Then we move this part to the other side and move this multiplicity to this side, so it comes dividing, this multiplicity to this side, so it passes dividing. And recall from calculus that the derivative of the natural log of a function of x with respect to x is 1 over the function times the derivative of f with respect to x. So we can identify that this term is the derivative of the natural log of GA, and this term is the derivative of the natural log of GB. So using this relation over here, we get this equality. So we have found then that this condition, the condition that maximizes the multiplicity of the total system, is reduced to this condition. The derivative of the natural log of the multiplicity evaluated at the energy UA with respect to the energy UA must be equal to the derivative of the log of the multiplicity of system B evaluated at the energy UB with respect to UB. So recall that this condition involves only one variable, the variable UA or the variable UB, because they are not independent. They are connected through the total energy. So we have found the condition that maximizes the total multiplicity. It is the UA that satisfies this condition. But this is not the language we use in physics. In physics, we express this result using another language. The language we use involves the definition of entropy. So entropy is defined as Boltzmann's constant times the natural log of the multiplicity. Okay, so we multiply both sides of this equation by Boltzmann's constant like this, and then this equality then can be expressed in terms of the derivatives of the entropy with respect to the energy. Okay, so now we can say that the energy of system A, in other words, the energy at which this derivative is 0, the most probable energy, is the energy at which the derivative of the entropy of system A with respect to the energy of system A is equal to the derivative of the entropy of system B with respect to the energy of system B. But that's still not the language that we use to express the energy that is most probable, the energy that maximizes the multiplicity. The language we use is in terms of the temperature, which is defined as the inverse of the derivative of the entropy with respect to the energy. So with this definition of the temperature, this equality is reduced to this equality. So we say that in thermal equilibrium, the temperature of system A is equal to the temperature of system B. And notice that since the energy of equilibrium is the energy that maximizes the multiplicity, in other words, it is the most probable energy, and since the entropy is given by the natural log of the multiplicity, then an energy that maximizes the multiplicity is also an energy that maximizes the entropy of the total system. So in this condition, the entropy of the total system is maximized. That's why we say that in equilibrium, the entropy is at a point of maximum, which is a consequence of the second law of thermodynamics. So to understand better how the second law of thermodynamics relates to this logic we have been developing, in the next lecture we're going to address the question, why does energy flow from a hotter to a colder system? So I see you next time.